Thank you. And well, so this starts out with the observation that data integrity is hard, and we'll just start with the side of it that it really matters for application programmers. Once we go down the file system and the device, it's even harder, but I'll spare most of the details unless they're interesting here. So how do we even make data we write to the system durable? And if we're talking at the syscall level, so the raw read and write calls, they're not persistent in case of a sudden power crash at all in any POSIX system, actually, in fact, in Windows as well, and in just about anything common. So we need to do another system call called fsync to persist it. There's actually another variant of it called fdatasync, which we're talking about. And the only difference between the two is fdatasync means we only persist the metadata that we need to find the data, so your blocks that you just wrote, while fsync persists everything. The only practical difference is that usually that fsync persists timestamps as well for typical updates, so in doubt it doesn't matter. Or we have the open options called osync and odsync, which are basically mean for every write you're doing, you get an implicit fsync or fdatasync for that range. So osync is the fsync, odatasync, the odsync, the data sync option. And if you're on crappy little operating systems like macOS or iOS, it's even worse. They're not going to persist your data if you call fdatasync. You need a special OS-specific call to actually flush the cache in the device. So good luck trying to write applications that don't power fail on macOS. Fortunately, most macOS systems these days have a battery in there, so it might not matter that much, but on a server, But thing is, even if we persisted that piece of data, it's usually not enough for actually writing applications that really care about the data, because even if we call fsync, or if we did our write with osync, odsync, the order of the writes is undefined. So if I'm writing down here, if I'm writing 4 blocks, the OS might decide I'm going to start writing the second one, then do the third, the fourth, and then the first, or any other order. But this example is pretty interesting because for a long time Linux did things like that due to bugs in the VM subsystem. So it's not just an example of what could happen, it's something that actually happened or still happens in practice, given that all the Android vendors are in the kernel from 10 years ago. So what are you going to do in your application if you want to work around that problem? And the typical thing is called the fsync and rename dance. So instead of trying to write to a file in place that someone finds, we write to a different location. We create a new file, some random file name that is not expected to be there, where we look for the actual data. And we write to that file by any mean we want. Then we do an fdatasync to make sure it's actually on disk in that form. And after that, we call the rename operation, which changes the name of one file name to another to put it back into the place where we want it. And then we do another fsync or fdatasync on the file descriptor for the directory that points to this file, because directory updates aren't really stable either in POSIX, so we'd rather have to do it. One fortunate thing of that dance is that rename, if there already was something on the place you renamed to, is implicitly deleted. So you can actually use this for updates too, and not just for writing new files. So canonical example would be, I have an important configuration file, etc config all the system, and someone changed a little variable out of the 5,000 in there. Think of all SUSE configuration distributions that had it. I just write it in a new place, make sure it's all there, swap it back into the place, delete the old one, and I'm done. But the issues with that approach is, one is the overhead is pretty high. Even if I change a couple bytes in a file, I'm going to rewrite everything, have space for being able to rewrite everything, which might not be a good idea. And the other problem is it can't really easily used with mmap. So applications do mmap.io, they map the file, they want to read it as memory. Some also want to write it as memory, which generally is very, very painful, but people like MongoDB try to do it anyway. And we can't really do that. I mean, if we remove a file underneath mmap, it will still point to the old file, even if the file has a new name by then. So if you want to combine this with mmap.io, you basically have to tear down all your in-memory data structures, unmap it, remap it. Well, actually, in theory, you could just overmap it and then rebuild them all again, which is so painful that no one does it. So there's solution number 2, which means keep a journal or log in the application. So instead of directly overwriting or writing a file, we have a simple little log similar to a file system journal. Databases have been doing this even longer than file systems, and have another data area that it's pointed to. The problem with that is, how do you know even your little journal entries are atomic and in order? So you need to stamp a checksum into it, a sequence number. Some people are very trustworthy, believe that their disk drives will do atomic updates of at least a sector, usually 512 bytes or 4K. The sad part about that is that all the traditional storage standards never actually agreed it. I mean, if you're an OEM and buying those, you will get it in your vendor agreements, but if you're buying an off-the-shelf disk, it probably does it, but no one guarantees you. But otherwise, this can be used if your application is smart, important, cares about performance and data integrity. So usually it's used for databases. But the biggest problem is really all of this is really, really non-trivial. You need to know what you're doing. You don't want your random app writer to try this in JavaScript because it's probably not going to work. And the other big problem is, because of the log, depending on how you structure the log, you do a lot of writes twice. So there's a lot of write amplification, which for hot drives might not matter too much because it's just a performance issue. But if you're on flash, which has a limited number of write cycles, this is a sure way to make your device not survive as long as it should do. And in the end, it duplicates a lot of the functionality that we have in the kernel in the file system anyway, but you have to do it again. So it's not just duplicated in terms of code, but literally in terms of the functionality. So you do the same thing twice. So what do we want to do instead? And there was a paper and presentation at the Usenix Fast conference in 2015. So about 2.5 years ago from Hewlett-Packard that introduced something interesting. It's called the atomic flag, another open flag that you pass to the open system call. And the semantics are defined. Roughly speaking, the details are, as usual, a little more complicated. Once you open the file with the atomic flag, every write you do is not just possibly not ending up on disk if you power crash, but literally is guaranteed to not end up in your existing place on the disk until you call fdatasync. So in some ways, it actually is a legal implementation that you previously had, except that it guarantees you the nasty corner case that previously no one hoped to ever happen. So what this boils down to is to update a range in the file, you just open the file, you add the new flag, then you write your data, and I used the pwrite system call instead of the write system call here to show that we don't have to write at some predefined offset, but it can be literally anywhere. And then we just need to do an fdatasync or sync call. Or if you don't want to batch updates, one other option would be you open it with osync in addition, which gives you the fdatasync call implicitly. So that means when your write system call returns, data is either all on disk or none of it if it fails. And, well, sounds like magic pixie dust, right? Pretty easy, but how is this actually going to work? Well, it actually turns out to be relatively easy due to things we did before. And the thing we did before is a feature called reflinks, something we have in a couple Linux file systems. So the first one we had was in Btrfs, but we also have it in XFS and OCFS2, a cluster file system. We can actually export it over NFS now and sort of over CIFS, except the semantics are a little bit different. And the idea is you can have multiple files, like a couple different inodes, as we call the low-level concept that the file is based on, that actually reference the same physical block numbers on the disk. So right now here, I've got like the two different inodes, and in that case, both of them have 3 extents that are exactly the same. So they all map from the same offset in the file to the same disk block. This is just the easiest case. This is what you get out of the copy tool with the --reflink option. It creates 2 identical file copies that share the blocks. It can actually be a lot more complicated. You could remap from one part to another, only share parts of it, and so on, but that doesn't really matter too much. And once we write to either of the files, the sharing gets broken. We allocate new blocks, update the extent map, decrement the reference counter. So it's pretty complicated in the implementation, but pretty simple to use at the API level. So, and to go into the implementation details a little bit more, what we end up doing in XFS, we have a concept of a file fork. So these are different parts of the inode that keep these sorts of logical to physical mapping. And the one that normally keeps the file data is called the data fork, pretty easy. And we introduced a new one called the cow fork, the copy and write fork, that is for every of these operations where you read from one block and now going to rewrite it to a different one because you have to unshare. We keep basically an overlay of the extent map in that one. And this is only done usually as long as the actual I/O is pending. So if we start the write system call that updates the area, we introduce the alternative extent map for that region, and then once the cache has been written back to disk, we can remove it again because we transfer the information in the block mapping and the cow fork into the normal data fork. So how is this useful for the O-atomic implementation? Well, we completely piggyback on that infrastructure. So for a file that we open with the O-atomic flag, we basically do 2 things. First thing is we set a little flag that says every write to that file should be treated like a copy and write file where we have to write out of place and later decrement the reference count on the previous block map. And it turns out that actually is much cheaper than doing the real reflink operation because there is no reference count. There's an implicit reference count of 1. We don't need to track it for something that wasn't previously shared. So the only real thing it does is it doesn't free the block yet when it's overwritten, but delays that. And the other interesting part is what we do when the I/O completes. So instead of normally updating the main data fork and on-disk extent map for the file once the write I/O completed, we do nothing. We just leave it stale in the alternative data map, don't update the real one, until the explicit fsync or fdatasync or the completion of the osync I/O comes in. So what we did after the write is, and actually I think I have some graphics for that might make it easier. So if we've got our little file, the blue bar is the file from, say, offset 0 to offset something really large, and we have our existing file before we did the data. And our data fork is going to cover all of the file. Literally, we always read it in together, so we have it fully covered, and the cow fork is empty. Actually, in practice, it's non-existent, and we only allocate it, but that's a minor detail I'm not going to put on the slides. So, and after we did the write with our O-atomic, all the data blocks in our data fork are completely intact, no change at all to them. But what we did was we allocated new blocks that are different from the old ones, and we tracked them in the cow fork. They're only in memory and in the log, so we can clean them up. In a case of an unclean shutdown, we can just throw it away. And then once we did the fdatasync, fsync, osync, final write-back operation, what we do is we move up the blocks we previously had in the cow fork here into the data fork, so same as we otherwise would do on the I/O completion. and we free the previous blocks that were there. Well, unless it actually is a reflink file too, in which case we don't free it, but just decrement the reference count on it. So what does this mean for performance? All sounds pretty complicated. Well, it turns out it's not that complicated, but despite that, the performance impact can be either really bad if you compare it to one thing, or really awesome if you compare it to something else. And the big question is, what are you going to compare against? So if you compare against the normal non-failure atomic file update, where you have the existing file, just override it in the same blocks and don't allocate any new ones, it will be a lot slower, because we have to call into the block allocator, which is pretty expensive, walk trees, find space, do transactions for it. But compared to rewriting the whole file, it's a lot cheaper, because you basically do the same thing, but a lot less of it, and actually do less transactions. So the performance is basically the same as writing to a part of a file that has been allocated before. So you extend the file beyond the previous file size, or you fill something, there was a hole in the file that never had a block allocation. The performance is basically the same. There's slightly more transaction overhead, but in practice it doesn't matter. And well, we have another trick to make some of this faster. And for that we go away from the file systems and talk about block devices instead. So if you're thinking of a traditional disk as your block device, the disk, just like the normal file systems, keeps overwriting the same blocks again and again and again and again and never moves anything around. In fact, even with a disk, it's not really hard, but a bit of a challenge to get your atomic 512 byte writes. But it's an even bigger challenge with flash devices. So if you think of an SSD or flash in general, flash, you never overwrite. Flash, you write, you read, and then you erase a big block, which means that when you have an SSD and you write to the same exposed logical block twice, the SSD is not going to write it to the same place. It's going to write it to something else, and it has to do something pretty similar to this. It writes it to a new place and then moves it logically back into the same space it was before. So when the NVMe standard came out, which is a non-volatile memory express, it's a standard for SSDs that are attached directly over PCIe, not over SCSI or ATA, or in fact these days over various network protocols. It introduced the concept of, well, it first introduced the concept of providing any atomacy for writes at all, which the previous standards didn't do, and it guaranteed that writes that are larger than a single sector could be atomic. So if you look at a typical enterprise NVMe SSD, it can write like 60K, 32K, and guarantees either all of the write made it to the media or nothing. And you will not get torn writes. And the interface for that is a little icky, because you don't tell the device this is an atomic write. It just guarantees in the little field that a firmware engineer could trivially get wrong that, oh, I'm always going to be atomic for if your write is not bigger than this and it's properly aligned. So I don't like that interface too much, but it's all we got. So how does this map to our O-atomic model? It turns out to the simple model I explained with the fsync, it doesn't map at all. But if we think of what we do with O-atomic and O-desync, it actually happens to map pretty well. So if I do an atomic write that is synchronous, I guarantee that by the time the write system call returns, either all my data is on disk together without breaking it apart or losing half of it, or none of it. And that's exactly what our NVMe block device offers. So in the little information system call where file system tells you that it supports O-atomic, we have different bits. If O-atomic is supported with OSync or without OSync. And for the block device, we can only support the O-atomic OSync. For the file system, we can support both of them. And the other limitation we have, which we'll actually get back to for the file systems as well, is that, of course, in the NVMe model, the size of an atomic write is pretty limited. But this is exactly what databases want. For example, MySQL can use this pretty easily. Or we can actually use it inside the file system. So if inside the file system we get a small enough O-atomic O-sync write, we can actually, instead of doing the previous scheme we did that allocates new blocks, just offload it to the block device. Yeah, what's the status of all of this? And this is where I've been lazy, because my plan was to have this all in the Linux kernel by the time I'm talking about. But after I first posted the patches in early 2017, I got about 15 million other things I worked on, and, well, haven't resubmitted it. The thing is, the code is very simple, and it's basically ready, so the really important thing without which I don't want it to go in the Linux kernel is to have really good testing for it. If you're talking about data integrity, data preservance, we'd much rather test it. And traditionally, the way to test this is to do manual testing, power fails, either by literally ripping a cable off or by having a breaker in. That's how people did data integrity testing for a long time. And we still need to do some of that. But what we really want is automatic testing of data integrity, log consistency. And it turns out just about the time I posted the first patches, people finally started to get serious about. So we have a device mapper log writes target in the kernel, which basically can lose arbitrary parts of a read and logs exactly what it did. And we have very interesting infrastructure built around this in XFS tests, where we basically have our automated test suite that can tell an interposing remapping driver between the hard drive and the file system to lose some writes here, tear up some writes there, do all kinds of nasty things a failing drive or a power fail could do to you. And we found a few really old bugs that probably weren't too practical, but they're in all the Linux file systems with it, and we've started to do a lot of testing for the refling feature with it. And now I need to write this up as well. What are the limitations of the whole thing? So one is, well, this model really should be useful for giving you really large atomic writes or multiple scattered and gathered atomic writes. Think of, you have an in-memory database that's doing I/O through mmap. So you've got your giant file mmap, and inside you've got B trees, LSM trees, dancing shiny trees, complex data structures from your resident PhD in data structures. And what you can do with that is update them here, there, everywhere a little bit, and make sure they're all committed together. And right now we're limited to updating up to 2 GB per single transaction, because that's a limitation of the transaction subsystem in Linux. But at least those 2 GB don't have to be in a 2 GB range. They could be over a 16 terabyte file, as long as you're not updating more than 2 GB at the same time. And the other thing, which is really important to get to as the next step, is support for DAX file systems. And that's another weird 3-letter acronym that I'm actually not even sure what it stands for. But what it is about is, if you think of persistent memory, non-volatile DIMMs, pieces of memory that are byte addressable or fake byte addressable because they're really cache line addressable, and you don't go through a page cache as normal in Linux. You don't cache data in DRAM when you mmap it and only then write it back to disk, but you directly map your persistent memory technology into the application. And this is like the crazy cool shit that every storage PhD is talking about right now. Not much has been delivered, but everyone's excited about it. This is why it's important to support it. And while persistent memory has all kinds of really great things, it has one annoying thing. It's block size, which is not a byte, fortunately, because if it really was byte addressable, it would be basically unusable, but it's cache line addressable, which for Intel usually means 64 bytes. So the only atomic write you can do is an aligned 64 bytes or smaller write, which is a total disaster for every transaction subsystem in the world, because they want this much bigger. And so people are starting to build all these crazy libraries that sort out that problem, build hyper-complex logging subsystems like Intel and SNIA are doing talks over talks over talks on this. And with a mode like O-atomic, you solve a lot of these problems because you still do your scattered little 64-byte writes everywhere, but you have a single atomic commit to move them back into place. So supporting this is really important because it takes a lot of the pains out of the shiny new world of persistent memory. The other thing that I said is like the block device support. I've done the raw block device support, but as mentioned, we should try to do this in XFS itself. And, well, that's basically it. It was pretty fast. And the other important thing you guys wanted to, so the second link here is the original paper I talked to. And what this is really great about is it shows various applications of it. So one thing they've been worked a lot with is a modified C++ standard template library, where you make the data structures it offers, and a lot of the programmers use persistent using that model with very, very little overhead, much less than a lot of the common key value stores. And that's the sort of programming models we hope this enables, because they are really nice even on an SSD today, and will become even nicer if we eventually get persistent memory and the physicists are finally getting their job done to make that memory really persistent. Okay. And now I really need a lot of questions because it was so fast.
Hello, thank you for your talk. Does usage of O-atomic flag result in higher file system fragmentation, and does it really matter? So
first answer is really easy, yes. Well, most of the time, but basically yes. Second answer is actually really, really interesting because we've not seen file system fragmentation matter that much on modern file systems, but despite that, everyone's got a defragmentation tool anyway. So if people really heavily use it, we might run into more problems with fragmentations, and we'll have to improve the defragmentation abilities. But in the end, it's the same problem as the basic raffling concept, which we're seeing more and more use cases for, or snapshots. So we're running into a lot more technologies that do out-of-place writes, which increase fragmentation. So we'll have to be carefully watching this.
Thank you.
Hi, thank you for your talk. What happens when the write is too big? You mentioned there's a 2 GB limit, fdata sync. Just how do you handle that?
So the previous version I had posted doesn't handle it at all. This is when I started testing it that I ran into it. And right now, the only really sensible thing we can do is return you an error from the fsync call. So I tried to figure out ways to do it during the write or doing the mmap page dirtying, but I couldn't come up with a good way to do it. So the only thing we can easily and reliably do in it is report it at the sync time.
I see, and then it's up to application code to close the file and reopen it and redo it in smaller chunks or something?
Or sync it out in smaller chunks, which is bad because it probably relied on the atomacy. That's why it would be much better to report it earlier on. But I mean, in the end, with so many guarantees, the application better get it right, otherwise it's screwed. I just really want at least to have a good diagnostic so people figure out what they got wrong.
Okay, thank you.
Next question.
As you might know, Linux kernel, I think Sagi is doing this. They're adding NVMe over TCP.
Yep.
How will your patches collaborate with their patches? Because what I might think, yeah, I'm atomic, I'm good. On the other end of the wire, he doesn't care.
Well, then the device should not expose it. And I work a lot with Sagi, so I wrote a lot of the original NVMe RDMA reference implementation. TCP, I'm only sitting on the calls but not doing any work. And so what we do for say the Linux NVMe over Fabrics target is we don't claim we can't do atomic I/O over a single sector. Now, once we have atomic in, we could trivially claim a giant size. The only problem with that is right now NVMe doesn't tell the controller, is this a write where I care about this atomacy or not? So we'd have to make it like a tunable, which would be annoying. So what I want to get to is go to the NVMe committee, and I'm pretty active in there, is like do a feature where atomacy for writes is optional and the host explicitly requests it wants a larger atomic write, because then we can turn it into per IO atomic flag in Linux, which we could do. So, I mean, right now, it's not a very nice interaction, but I think it's mostly the NVMe protocol's fault. But as I said, I'm active in the working group and thinking about ways to fix it once we've made progress with this.
Yeah, microphone only. But this will, I mean, you're saying 2 gigabytes as an atomic write.
Yeah.
And, well, TCP is cool to some extent, but this means that on the target side, the host, the target needs to cache all the data, wait until it's actually received, because you might, you know, for whatever reason, in the middle, one packet with this, with number that, I don't know, is has a lot of zeros or whatever.
Okay, so here's the different things. I mean, for now, we just talk about O-atomic in the file system, and then we move over to atomic writes in NVMe to keep the concepts a little clear. So if we run this scheme where the file system is in control over a network protocol, like NVMe over TCP or iSCSI or whatever you want, the protocol doesn't matter at all, because we're going to write all this new data, but it's in different blocks. And then we do the atomic commit to switch it in, which literally only requires you to atomically handle a 512-byte write as a normal block protocols. Now, if we want to expose like the NVMe larger writes or atomic feature, which usually only goes up to a few kilobytes, all of that indeed has to be buffered in some form. But the form could be to literally do that in the device, which is what a current NVMe controller will do, right? I mean, if you're doing a write in an NVMe controller, there's no any write, because there is no atomic. What it always does is, if now this instead of a file is your NVMe namespace, your block device, and you want to update this range, say blocks 250, 255. What the NVMe controller will do is, it will take the write, it will write it to some other physical space than where this is, and by the time the write completes, switches it over. So it basically does the same, not exactly, but very similar underneath. Now, if you want to increase these sizes, you run into the problem we had there before with fragmentation, because you probably want a giant block in your 2 gigabytes if you support it, and you run the problem that you're probably not really going to buffer the data, because it's much easier to redivide it in flash, but you just need a lot of free space somewhere. So for a real NVMe controller, I don't see these sizes to be giant. They might be growing a little bit, but they're probably not going to be in the gigabyte range anytime soon. Yeah, 1632, 64K is pretty typical.
Okay, thank you. The next question.
Nowadays, a lot of organizations, especially in financial area, using locks to protect their data. Are there any techniques to like atomic in locks, and are there any work in progress for this case?
What you said, using locks?
Locks.
Do you mean file locks or in-memory locks for thread?
LUKS. Locks. LUKS.
What?
No. Maybe I'm not pronouncing this right, but LUKS is a technique to...
you mean encryption?
Yes,
like
encryption.
on disk encryption.
To encrypt the data. So are there any techniques such as atomic being going to this sphere?
Okay, so the nice part about the file system implementation is that it really doesn't care what your block device does underneath. So it can encrypt, it can remap, it can do parity rate, it doesn't matter, as long as they satisfy their minimum atomacy guarantees for a single block.
But how will a file system will know that below the locks is NVMe, for example?
Oh, okay, so if you want to use the hardware offload, it's probably not going to work, and it's probably not going to work for the foreseeable future. On the other hand, already a fair number, and it's only going to increase in the future, NVMe devices are going to support encryption in the device using TCP OPOP. So if you trust the device vendor enough to rely on that, you won't need software encryption and can rely on the device.
Okay, thank you. The next question. I have a question about fail chain application. Application started a transaction, but changed its mind and want to tear it off. How it can be done?
Okay, so on the implementation side, a rollback is pretty easy because, as you see, we never overrode existing data. Right now, we don't have an explicit interface for it. You right now can get it by closing the file descriptor. That throws it all away. In the future, we could think of another rollback system call that takes a range and says throw it away just for that range and don't undo everything.
Thank you.
Okay, the next question.
Okay, so you mentioned that, for example, XFS can support some NVMe features inside it, so it can run faster. But this will require some, if any other file system that will support Atomic in the end, will require some like the same subsystem inside it. Are there any plans about maybe moving Atomic support for block-like devices in Linux in separate subsystem rather than using in the concrete file system itself?
Yeah, actually there is, I mean, as I said, I haven't even implemented that for XFS yet, only for the raw block device if you use the block device node. That support is very simple, mostly because of the weird interface in NVMe. So what we do is we read from the device what is the alignment and maximum size you require for atomic writes. And then the only flag we set on the BIO, on the block device, IO submission structure is a don't merge, don't split. And that's it, because there's really no atomic flag on the protocol level, so having that in Linux would be kind of weird. That might change once we get better protocols for it, but that also means the amount of file system code to support it is actually not going to be much. It's basically if this is aligned to what the block device accepts atomic, we just do nothing. So it's very simple. The real problem with that is testing to make sure it actually works. It's not writing the code. So we'll have to retest this for every file system, but the amount of code is very minimal.
Thank you. The next question.
Hello, thank you for your talk. I have a question. How can we know how much data we have not synced? If we talk about a limit for 2 gigabytes, we want to know how much data is already not in sync. Can we know this somehow?
Sort of. So we keep a counter how many bytes, or actually how many blocks, but the bytes are easily derived from that, or in the cow fork. The only thing you need to remember is actually this will not just include the atomic write operations, but this will also include anything for which we do a real copy and write, right? You can still do your atomic write to a file that is shared. I don't think it's a usual use case, but it's the same mechanism. So you might get a higher number than you actually had, but you will never get a lower one, which probably is okay.
Okay, thank you.
Thanks for a nice talk. You said that you have a plan to develop a test for it.
Yeah, I've already started, but I've not gotten very far to do the automated testing. I've done a lot of manual testing before.
And this involves some simultaneous operation and so on. Do you have plans for some unit test, fuzzing, I don't know, because race conditions are awful.
Well, so I mean, there shouldn't be any new, and should is always a good word to say, there shouldn't be any new race conditions because all the mechanisms to implement it are literally shared with a reference code. So we might as well have race conditions in there, but they're not completely specific to this. It turns out the reference code is the most heavily tested file system code in Linux because the guy who led the development, I did some of it, but most of it was done by Derek Wong. And he's just crazy about writing tests. And they're not really unit tests in the sense how a Python programmer or Java programmer would use it, because that's very hard to do for something that deals with persistency, very hard to isolate. So they're more in the category of integration or system tests if you want to do hard classifications. But a lot of the operations are more that of a unit test. So there's all kinds of stress tests. There's basically trying to test for above it or below specific limits of the implementation and converging operations. So I'm very confident about the test coverage of that code. In fact, as I was like the second to lead developer, I put it in production for a customer right after we landed it in the kernel because I was so confident of the testing. And we found a few bugs, but not many and none catastrophic.
Thanks.
And I want to have a similar coverage for this.
Cool. So, thank you. Next one.
Hi, thank you for the talk. And you speak a lot about atomic in XFS. What about other Linux file systems?
So if your file system already does out-of-place writes, it's reasonable to support it. I'm probably not. I mean, the most obvious one that should be able to do it would be Btrfs, but the code is such a mess that I personally do not want to touch it, but there might be other enterprising souls. It should be pretty similar, easily doable for OCFS2, the cluster file system. And otherwise, in tree, we have two log structure, sort of log structured file systems, F2FS and what's the other one, NILFS2. I suspect they should also be able to do it, but it might be a little more complicated because they don't really have that concept of copy on write, even if they're always writing out of place. And the UBFS, the flash file system, is also doing sort of out-of-place writes, and I actually talked to the maintainer. He's interested, but it's not anywhere near the top of his to-do list.
And what about X3, X4?
Very little chance. I mean, they'd first have to do some mechanism for out-of-place writes, which they don't have in progress. So once they have that, it's a natural small add-on feature, but you first need to do all that big work. I mean, XFS reflink work took about 2 years, with 2 persons spending a lot of time on it and a couple others assisting.
Okay, thanks.
Next question.
Christoph, I have a question. In the original paper from HP guys, O-atomic was the first part. And there was a part about some kind of syscall they introduced to deal with multiple file, syncv or semi-octal. Are you planning to do something like that for multiple files?
Unlikely, because I've not found major use cases. I have all kinds of use cases for that. And the other thing is, we could do it in terms of mechanisms, but A, the interfaces are ugly, and B, the limitations will just show up more nastily with that. I mean, even with the 2 gigabit writes, we're basically pushing the limits of the logging subsystem. So if you do more files, you get even more logging overhead. Then you need to scale the amount you can do per file down. Then once you do operations on multiple inodes, you start to get into deadlock territory without very clear lock ordering rules. So it's a lot more complicated, and I've seen a lot less use cases for it. So I'm not going to say no, but it's not currently on the to-do list.
Thanks.
Okay, if we have no any other questions, what's the best one you receive from the audience? What is the best question?
Pretty much all of them were pretty good, so I don't want to rate.
We need to select.
It's definitely the best questions I ever had at a conference. I mean, A, very qualified, and B, I think even without that, the most.
Okay, thank you. Thank you very much. Thank you.